Okay, so let me introduce Rao, the man who does not need any introduction. Rao obtained his PhD degree in computer science from the University of Maryland, College Park. After a brief postdoc at Stanford, Rao joined as a faculty in the computer science department at Arizona State, becoming a half professor in '96 and a full professor in 2000. And he's still expecting to become two professors soon. Rao directs the Johan Research Group, which is associated with the AI Lab at ASU. His current research agenda revolves mainly around human-aware AI systems. He is a recipient of many prestigious awards, including NSF Research Initiation Award, NSF Young Investigator Award, College of Engineering Teaching Excellence Award, an APM Faculty Award, and multiple 4 Google Research Awards. Among many other recognitions, he was named a Fellow of AAAI in 2004 and elected a Fellow of the American Association for the Advancement of Science in 2017. He has been an invited speaker at multiple conferences starting way back in AAAI 96, HK, ICAPS, and building up to today to PRL workshop, which all of these instantiations of that workshop he participated in so far. So without further ado, we're really happy to have you here and looking forward to listening to your talk. And I hope I didn't miss any words. Probably did.
Okay, so can you guys hear me?
Yes.
Okay, great. Okay, so as Michael said, I did attend all of the PRL workshops. So I have some idea of what you guys have been discussing in the past several years. And in general, it's always a little intimidating to speak at ICAPS because you guys know what I'm talking about. Oftentimes invited talks work because the attendees don't know what you're talking about. But so be it. I am going to try and hoodwink you today. So I'm going to talk to you about planning to advise and explain reinforcement learning RL. Let's see if I can get this. Yeah. So you guys have been talking a lot about the bridge, right? So the planning RL and you want to build a bridge. And building this bridge is kind of tricky these days because we seem to be having RL and be meeting obliviousness of planning all around. So you have NASA and Schlumberger and various other people who actually have any kind of sequential decision-making problems using planning and OR techniques. And so they don't seem to be using deep reinforcement learning techniques, thankfully, yet. And yet, we are a lot more impressed by these guys essentially walking on the tessellated grids, essentially learning how to walk and so on and so forth. Both are important, I guess, but it tended to be the case that the planning has looked at, the applications on the right-hand side and the RL, AlphaGo notwithstanding, has mostly looked at the applications on the kind of left-hand side, as you saw, for example, in Sergey Levine's talk. So you guys want to build a bridge. And so the question, of course, is how do we build that bridge? And I sort of, pardon me for actually copying a whole bunch of tweets all through the talk. I keep thinking about this planning RL dichotomy, which doesn't make any sense at some level because, I think Bernard Shaw said England and UK and US are two great countries separated by the same language. And similarly, I think planning and reinforcement learning are sort of two central areas of AI separated essentially by a common problem. And yet there is enough of differences in the terminologies that a whole bunch of people basically miss, the important differences and wind up trying to reinvent the wheel. So Even though my main talk is going to be about the specific pieces of work that we have done and published recently on advisable and explainable reinforcement learning using symbolic planning techniques, which is the second part, do allow me to indulge me to teach a little about planning versus RL, sort of from a model-based perspective, because, as I said, I did come to this workshop, pretty much the last couple of years, as well as parts of it today. I was just too busy trying to complete my talk. But I do think that there tend to be some unnecessary confusions, and it might be worth just getting them settled once and for all before we start, so that things will be easier to talk about later on. So, of course, as soon as people talk about planning versus RL, people tend to think in terms of model free versus model based. And I'll tell you that that's really not the only important dimension. And from the ICAPS perspective, that's not even the most important dimension of a difference. So let's get started. Planning versus RL, the atomic story, basically, think in terms of the atomic state spaces and so on. Obviously, you guys have seen this. Some of you are aware of it. Some are probably, kind of may or may not be, completely aware of this. But essentially, planning goes from a model of the dynamics and the initial state and goal state and tries to compute the policy. And RL tries to go directly from the agent's experience in the real world to try to compute the policy. So if you still look at that circular diagram from Saturn's book earlier, from God knows how long back, essentially the RL just tries to go from experience to value policy, and the planning part is like an intermediate step, which has some advantages in some cases, essentially. And so from the experience, you can learn the model and use that to do planning. In particular, model-based RL allows the agent to do mental simulation, whereas model-free RL basically just does it like that Nike commercial. So upfront, all the training has been done, and the policy just basically looks at the state and does the action. So there's very little online computation, which actually is kind of interesting because, from the perspective of planning, old times back, there used to be this idea called universal planning, which was considered a universally bad idea. And universal planning is essentially a kind of model-free policy learning, a model-free policy on steroids, essentially. Although pure RL is supposed to learn from direct experience, in non-ergodic real-world domains where you might actually die, you might actually get stuck, and so on and so forth, RL techniques have also been applied to known but intractable models, represented sometimes by actual symbolic models and sometimes by simulators. And in this subclass, we need to keep in mind carefully, because in this subclass, RL is really a weak and lazy method. If you are doing well with RL in these classes, it's not because RL is good, but because you could think of better heuristics using the model. So you should really be able to do much better in the case of known models that are intractable. And we will talk about, as I said, saying that RL is a weak and lazy method is not an insult. It works all over the place. But when you have a lot more knowledge, using weak method is essentially quite ineffective and inefficient. Okay, there's a whole bunch of glossary we can talk about. I basically want to just remind people that, of course, plan and policy are the same on both sides. By planning, in planning terminology, we tend to think of a domain model. They tend to think of, in RL, we tend to think of transition model. It can also be provided through a simulator. Although in planning also there's been work that used simulators separately. When I say planning without any qualification, I mean ICAPS planning of the kind that the majority of the people do in this conference. So goals, rewards, goals, trajectory constraints, references, everything else goes under the guise of reward metric. So essentially all of those just get compiled down to reward metric. And so saying reward is all you need is sort of like saying Turing machine is all you need. Yes, but so what? I mean, really, you may want to provide a lot more expressive language to represent what it is that you want from your decision maker. And then one other thing that people sometimes get confused about is, heuristics in planning essentially can be thought of in terms of reward shaping in RL. You add like a little reward to the real reward, and you want to still hope that the policy is optimal. That's like basically saying if you add the admissible heuristic, your final policy will still be optimal. This is something that's worth keeping in mind. People tend to think of model-based versus model-free as like the main difference. In fact, I just read a paper where they actually said in the very front page that's like a main difference. But really, yes, planning uses models, while RL can obviously get away without models, by being model free. And yes, models are a way for RL to amortize the cost of learning about its environment. So you actually provide the model, then you essentially can avoid relearning the transition dynamics, for example, every time you work in that environment. Okay. And so this is something that planning people know already. We actually start with a domain model and we don't keep trying to ask every time, what did you say this blocks word is? Because you just have the domain model. But the models in planning, AI planning, actually, they differ from the models used in RL in a more important respect, which actually is relevant to things that I talk about here. Models learned in RL may or may not be interpretable. They may be internal dynamic models, such as the things that go from one pixel state to another pixel state using some latent features which you, the user of the decision support system, have no idea at all. So in those cases, essentially, models may reduce sample complexity, but they certainly don't allow for interpretability. Whereas human-given models, which I think our community tends to spend a lot more time over, they can provide declarative biases for RL. They can actually provide interpretability out of the box, but they have their own disadvantages, as you know. So to come back to this planning versus RL, I want to now actually talk about AI planning versus deep RL. When people talk about RL these days, mostly they think in terms of deep RL. And when we talk about planning in this group, we talk about AI planning, quote unquote. I hate that term, but that's how become the standard. In the non-atomic case, we do need to talk about representation of states. And when you talk about representation, you have to ask, whose representation are you talking about? In this case, AI planning focused on explicit knowledge tasks, and it basically starts with human-given domain models. And so representations are ipso facto, that is, as given, interpretable at some level to the humans. Whereas in the case of RL systems, for explicit knowledge systems, there is a choice. RL can either use partial models seeded by the humans, human radial sorts of models, and improve them, or they just decide to learn their representations from scratch. When many of the people are doing pixel dynamics models, for example, from Block's world, they are saying, screw your model, I'm going to learn whatever I want to learn about this domain myself directly from scratch. For tacit, so there is this choice, and of course the trade-off in the choice is that the first one is more interpretable, but in fact there is this worry that the model that the humans, representations that humans give are not good enough, and you could provide improved performance if you learn your own representations. And then if you learn the representations from raw sensory data, then they can be quite uninterpretable. There's no real reason why internal models learned by a deep reinforcement learning system or a deep learning system should be interpretable to the humans. You have to actually do this extra step of making them interpretable if you care about that, which I actually do. For tacit knowledge tasks, they basically have to learn their own representations because humans are not ready to give anything. So for people in RL who tend to mostly work on tacit knowledge tasks, and I think Sergey was actually, many of the earlier parts of Sergey's talk this morning, for example, in robotics and manipulation, etc., they tend to be about tacit knowledge tasks where you don't really know how you walk, you don't know how exactly what angles and paths you have to put at the 20 different joints you have so that you don't fall down. And so in that case, you might as well let the system learn. And you're not going to ask the system ever, why exactly did you put the joint number 17 at a 23.7 degrees angle as against 29 degrees angle? You're just not going to bother about that. You only care about probably other kinds of interpretability, such as why did you break this vase? So to complicate matters further, as nice as this explicit versus tacit knowledge distinction is, the complicate matters further. Most real-world tasks are actually hybrid, with aspects of the explicit knowledge in the top levels and tacit knowledge in the bottom levels. And this sort of also became clearer, as you can see in many motion planning, task planning combinations, including this morning's talk. So I don't have to belabor this. Planning people always believed in doctrine. They believed in symbolic models. We have actual languages for talking about the domain models, domain knowledge that we're going to give to our planners. Explicit knowledge in planning actually in the past used to be more of the thing that I would argue against. That basically back in ICAPS 2003, I basically was haranguing people saying, you can't possibly be asking for so much domain knowledge that there is no planning left to be done. And so, there are some kinds of HTM planners, for example, that are asking not just the domain dynamics, but also search control knowledge to be embedded in the domain model. And, if it's not easily available to the humans, forcing them to give it seems to be a kind of a silly idea. But then, as you know, lately, we have gone, the pendulum has swung, and we are actually more interested in not using any kind of knowledge and trying to get it from scratch ourselves. I did talk about this at length in, I think in 2020 in the DC doctoral consortium called Polanyi versus Planning, where I mentioned the fact that tacit versus explicit knowledge and the fact that AI planning techniques tend to focus on explicit knowledge more of the time. And that just as it's kind of silly to force humans to give knowledge that they don't have access to, that you should really be spending time doing search yourself, it's also kind of silly to spurn humans who are ready to give you knowledge about their domain, say, no, we're going to just learn it from humongous amounts of experience data, from simulators in particular. By the way, actually, most of these RL systems don't really work in the real world, as you all know. They tend to depend on the simulators. And the problem, of course, is simulator is a kind of a black box model of the real world that has been provided to you so that if you die in the simulator, you don't actually die. You can restart your life all over again. If you die in the real world, like the car is about to, it's dead. It's basically only the other people surrounding it can learn what screw up it did. So it's highly unlikely that for explicit knowledge domains, simulators are actually easier to provide than partial domain knowledge. And so insisting on simulators just so you can't be accused of any human given knowledge is a bit perverse in my view, because I think sometimes writing the simulator actually might take longer time than providing the model at a partial level of abstraction. This is an interesting connection that some of you might actually enjoy. I won't go into too much detail, but if you are actually provided the simulator, if you're thinking of simulator versus model, when you have the model or the simulator for the domain, that means it's actually the system is not working in the real world. It's working either off of a symbolic model or a simulator. Then the difference between planning versus reinforcement learning in that case really becomes the difference between SAT and CSP. SAT basically looks at declarative clauses, and CSP says, give me any piece of code that can take a partial assignment and tells me whether or not that partial assignment is still consistent. And so it turns out that there are some advantages for CSP model, there are some advantages for SAT models, but neither of them are a definite win. And neither of them are a definite win. So similarly, so that's something that I want you to keep in mind, that in fact, when the model is known, RL really is a weak method, and you may not necessarily want to say that RL will do better than any planning approaches. This should not be surprising. I think last year, some of you may have remembered that there was this 4 paradigm folks who ran a competition for scheduling tasks, which is really a classical OR planning-age problem. And they were hoping that some RL methods will be provided for this situation, for this particular problem. And then they found, to their consternation, that the winning entries essentially did not use RL. And so they were actually, towards the end, they were saying, we should make the next iteration be more friendly to RL. That seems kind of silly to miss the point of important differences between RL and planning. So coming back to the elusive bridge, In the case of AI planning, it's been used mostly for explicit knowledge tasks, where the humans provide flexible, interpretable models, and the system searches for the best policy within them. And given that the models are human, given policies are more or less interpretable. Although, of course, there's a lot of, just because you can make sense of the symbol doesn't necessarily mean you can understand the combinatorics, and you still have to provide certain levels of explanation. But you're starting from a much more shared vocabulary standpoint. In the case of reinforcement learning, essentially, model-based reinforcement learning assumes that it can learn the model from experience, and these models may either be seeded with partial models representations provided by the humans, in which case they will be somewhat more interpretable, or learned from scratch, in which case they may have better performance. In fact, if the humans don't understand the domain completely, their representations might be hobbling the solver. Whereas if the solver learns things from massive data, you can actually find insights that the humans have not been able to capture. So that is like the first part. And then the second part that I want to talk about is basically, given that I have this planning is about explicit knowledge tasks, and RL is much better for tacit knowledge tasks and learned models by itself. So the question is, either I can force RL to use knowledge-based models that the humans have provided, or we can say, you do whatever you want, but you should be able to take advice from me and provide explanations to me at the same level of ease that normal symbolic planners do. Okay, so that's the steps that we take. So making RL advisable and explainable, even with its own inscrutable models, is what I'm going to focus on. Sometimes actually learning inscrutable models when a model is freely available is a dumb idea, as I pointed it out to you. But I'll assume that you chose to do that, and I still want your decisions to be making sense to me. And so you need to take the responsibility of taking advice from me about my preferences and providing explanations if I need. So I think I'm not being particularly controversial if I were to say that I want AI systems to be explainable and advisable. We are increasingly surrounded by these systems, and we want at least the decisions they're making to be understandable. And oftentimes, there are preferences that humans have that may not actually be explicitly known to the system upfront. And so you should be able to advise the system at least about your preferences, and you should be able to understand its decisions. And so for alignment case, for concordance with our preferences, as well as sometimes efficiency, I might tell the system things that might make the plan more efficient, or the search for the plan or the policy more efficient. The explainability and this advisability, when you are interested in that, they should be on that is human terms. We shouldn't have to debug AI systems to interpret them. It should be a pity if, in fact, all the progress in AI results in us humans going into the incomprehensible land of some deep reinforcement learning system and trying to figure out what the heck it is doing. That would be much worse than the early mixed initiative planning, where humans would go into the search queue of symbolic planners and try to rearrange the search queue. That's kind of very sad too. That's a bad way to live life. So we argue that basically systems should support a symbolic lingua franca, and for decision support systems, this lingua franca has to be, basically in terms of symbolic planning. That's my main takeaway for this second part, and I'll show you some examples of the work that we have done that actually uses that. I do want to mention that the moment you say symbolic, as well as a system that is possibly using neural networks as deep reinforcement learning system, there's this issue of neurosymbolic AI, and I kind of want you to distinguish in your mind between two different motivations for neurosymbolic approaches. One is internal symbolic reasoning. That means even if there is no humans in the loop anywhere, the system might want to come up with abstractions of presentation it has learned just to improve its performance. That might be possible, but if it basically is finding symbolic abstractions of the representations it has learned, those symbols don't have to have anything connected to the symbols that the humans actually think in terms of. So there's no real reason why, as Wittgenstein said, if a lion were to speak, you would be able to understand, because there really is no shared vocabulary, there's no shared experience. The other case is symbolic communication interface, which is what I'm a lot more interested in. I'm saying you can do your internal reasoning any which way you want, but I, the human, should be able to give you advice in terms of preconditions and effects and which action to do when in terms of giving advice. And you should be able to give explanations to me in terms of why you did a particular action instead of a different action, in terms of the missing preconditions or violated effects or something. And that's the kind of thing that I'm talking about. So symbolic communication interface is what you're looking at. So there's a bunch of work that we have done earlier on in terms of what it takes for even a symbolic planner to provide explanations to humans in the loop. That is the thing that we have done beforehand. Is a book and a monograph out there for symbolic planning models. So this is where even if in fact you share symbols, even if you share symbols, you may still need to do some heavy lifting to make sure that you are providing explanations with respect to the differing symbolic models that the humans might have in mind. They might have a differing preconditions and effects, for example, for the same actions than what the machine thinks it is supposed to be. So that we have done that. I'm not going to go over that. But for this particular talk, the more interesting part is what happens if you have vocabulary mismatch too. That means, in fact, the machine is essentially not thinking in terms of any concepts that the humans are thinking about. So you need to then provide a vocabulary mapping. So the lowest common denominators for humans and AI agents typically tends to be just raw signals and data. So if you are a deep reinforcement learning system looking at a pixel, an image, then pixels are the common, substrate that the humans and the machines are looking at. And not surprisingly, explainable machine learning has been thinking in terms of things like saliency regions in the pixel space. My general stance, and I've talked about this in other places, is that it's kind of very sad to have to get by with pixel-based, saliency-based explanations. First of all, very few people ask explanations about images. They ask explanations about decisions in a sequential decision-making problem. And in the case of sequential decision-making problem, you almost have to provide a saliency region over the video of your life or the video of the entire world, saying these space-time signal tubes were the reasons why I had to do this particular decision. And that winds up imposing very high cognitive load on the human. So those kinds of explanations are extremely hard to give. And those kinds of advice is also extremely hard to give. Providing advice, by at the pixel space is very hard to give if you're thinking about the domain in objects and in relations between objects. So what we've been basically, as I said, pointing explanations are actually pretty hard to comprehend. And so there's a IIII 2022 Blue Sky paper that just we presented. That's what I'm trying for the rest of the talk, where we basically argue that pretty much any decision support system, any AI system, and especially decision support systems, as far as we are concerned, sequential decision support systems, they should, irrespective of what they think, what representations they make up, etc., they should provide a symbolic interface, a symbolic quote unquote, more than an API to the humans in the loop, such that they can provide explanations through in symbolic means and take advice in symbolic means from the humans. And that will allow for humans to actually improve the speed up or to make sure that their preferences are given to the machine in symbolic terms and also accept explanations in symbolic terms. And so that can actually provide a nice interaction, cyclic interaction between humans in the loop with the machines. So that's basically the thing that we do. In particular, I want to talk a little about accepting advice, a couple of papers, and providing explanation, one more paper, and then end. So in the case of accepting advice, essentially, irrespective of what the deep reinforcement learning system, in this particular example that I'm talking about, I'll be looking at a deep reinforcement learning system, it might well be having internal representations that don't have any connection to what humans think of about a particular domain. And so the humans might be giving advice in terms of objects and predicates and actions, and it should be able to convert that into terms that might makes sense in its internal symbolic representation. So if I'm basically thinking in a different language than what you guys are thinking, then I'm actually producing those thoughts in that language, still converting it into the language that you can understand so that we can make sense to each other. So there's a New Rips 2021 spotlight paper called where we talk about this expand system, which looks at this human advisable reinforcement learning problem, where when during the reinforcement learning, time frame while the system is being trained, the agent, the humans can provide feedback about whether decisions are right or wrong, either from the point of view of efficiency or from the point of view of safety considerations. And you are providing that decisions. And the question then is, so when given a pixel state where the system is doing the following action, the human gets to say, no, not this action, this other action. That's the first part. And more importantly, they get to say, the reason this other action is better is because, and provide an explanation as to why the advice is more relevant. And this explanation used to be in previous systems in terms of pixels, by actually annotating regions of the images. We support essentially object-based explanation. So basically you say, don't do this action because there is a stop sign, for example. Don't do this action because there is a ways. And the system essentially then gets to convert that object by itself into the pixel representation. So the system does the heavy lifting of converting denotation of symbols into the pixel space. And then once it does that, it can also do other crazy things. In this paper, for example, it increases the number of examples by essentially keeping the region of that object in the pixel space constant and disturbing the rest of the pixel space, so that you have more and more examples where hopefully the correct action is still the one that the human has provided. So this is sort of a context-aware data augmentation. With these sort of ideas, actually, we could show that, in fact, the system actually does much better in taking human advice. In this particular case, actually, human advice is meant to improve efficiency. So the sample complexity is better. It turns out that the same kind of ideas can also be used even when, in fact, the task under consideration is a tacit knowledge task. By the way, I should mention that in the previous case, we were looking at Montezuma's revenge, which is actually both a pixel-based approach, but it also has like a symbolic representation that the humans think in terms of. So the system is thinking in terms of pixel-based representation, our internal representation, and the humans are thinking in terms of the objects and so on. Even in the case of things like grasping and robotic kind of tasks, we actually showed in a paper in February 22 workshop that the demonstration that a human provides can be maybe ambiguous, but you can reduce the ambiguity in the demonstration by trying to parse it in terms of the symbols and the actions that the human model might have. So that sort of reduces the amount of ambiguity in the advice that the humans are providing. The other type of advice that actually was just presented a couple of minutes back, I believe, in PRL, is essentially, what if instead of doing on demand, this is the right action, this is the right action, I want to tell my RL system, here is an approximate model of my domain, deal with this and try to make policies, that are kind of consistent with this, and hopefully, so that you can do training much faster. So when you're doing this kind of integrating symbolic planning models into RL, where essentially the planning model is kind of seeding the RL's model, one big worry is, what if the model is incorrect? This is kind of the thing that people say, well, if the humans provided it could be wrong. Yes, it can be wrong, but it's better to take advice that is potentially incomplete and incorrect, but it's given by the humans, and try to work as far as you can with it as an RL system, than to just say, I'm just going to ignore everything and start from scratch and try to look for policies myself and hope that they'll make sense to you. So if in our case, basically this paper is actually a nice marriage of ICAPS planning and RL systems. We basically use an incomplete, incorrect model potentially, where there's no requirement that the model be incomplete, correct, or complete, and basically act as if that model is correct. Extract landmarks and assume that those landmarks and their orderings are going to be preserved by at least one plan in the real world. And so the RL system then is going to be looking for options or sub plans for each of the landmarks and basically tries to come up with diverse set of options for each of the landmarks, because the minimal obvious plans may not actually work out because there are many details that may have been missed in the incomplete, incorrect model. And so you take this diverse set of options that you learn and you actually put them together using meta controlling. That can be used either by a combinatorial search or an RL system. And we actually show, just like the old strips is complete for serializable domains, but when are domains serializable, it's if in fact strips can solve them. Similarly, we actually come up with a theorem saying MVTR conditions where that if they are satisfied, which basically requires that at least one plan would satisfy the landmark orderings, then that would be enough for the system to be, RL system to be able to come up with a policy that is consistent with the model. But then figuring out whether or not it's MVTR essentially is actually checking whether RL system has been able to find it this way. So, in terms of looking for the diverse skills, the RL system learns the skills for each of the landmarks separately, and then it tries to make sure that the skills are diverse in the sense that they use different actions, presumably, and in coming to the same landmark, so that they can be combined together into a global plan. And if we have a complete model, this is sort of like finding non-minimal plans for individual subgoals, so that those subplans can be merged or serialized together to solve the overall problem. There's an old ICAPS 96 paper that I have that actually talks about that idea. And then here we are doing it in the context where the model is not complete. So there is actually a beautiful, deeper marriage between the RL and planning ideas. Once again, we did experimental evaluation. One of the nice things about this is this idea works even if the RL is actually not using any symbolic models at all. All it needs is a kind of a classifier that tells whether or not the state satisfies a particular fluid or not. And those can be learned. That's basically how we do the symbolic interfaces. And again, experimental results show that this idea actually does better than the RL going on its own and trying to do things from scratch, and also with respect to some other competing approaches. The last thing I want to mention is the explanations part, where essentially, if in fact, the planner, the RL system comes up with a policy or an action in a particular state, and the human is not happy with that, and they might provide like a foil and say, why didn't you use this action in this particular state? And again, this is the Montezuma's revenge problem. And so the idea there would be that the foil would to actually provide the explanation for the foil as to why the foil is not feasible. The planner learns a local symbolic PDL model. The planner actually, so the RL actually is not doing PDL. RL is basically doing whatever the heck it wants. In our case, it was actually using RAM states because the RAM states are possible for the Atari games, but it could have been doing deep reinforcement learning. It could have its own internal representations, but on the spot at that point, it actually generates a local symbolic approximation of the model around that decision, and then uses that to say, well, I can't do this because a particular key condition for this action is missing in the current state. So the explanations are still in the language that the humans can understand. And we, in ICLAIR, basically, this year we presented this paper, which basically talks about how the local symbolic model is computed through sampling online at the time when you are actually providing the explanation. This is sort of like, those of you who know XAI literature and the LIME system. LIME system provides local linear representations. Here we are doing local symbolic representations around the decision. We also get to actually compute the confidence level. The RL system gets to compute a confidence level for this explanation. And so that sort of takes into account the fact that you're thinking in one representation and providing explanation in a different representation. What if you're making everything up? So these confidence levels try to capture the kind of the accuracy with respect to the machine of its explanation. Again, in the case of empirical evaluation, the bigger thing that we focused on is, humans in the loop happier with the symbolic explanations or the saliency-based explanations, and the results are that they tend to be happier with symbolic explanations. There's a bunch of open research challenges in making this symbolic interface work, including collecting the initial concept set, grounding the concept set, basically using classifiers, and also expanding vocabulary, either from the RL side, saying, give me more vocabulary items because my saliency region cannot be approximated by the fluents that you have provided me. Or telling the human new fluents, which is actually the kind of thing that might happen if, for example, AlphaGo is trying to explain the reason for its infamous 33rd move to the humans in the loop, where you are essentially teaching new vocabulary items to humans. So we actually talk about this in that, the Blue Sky paper about these challenges and how the concepts are, initial concepts that are, for example, taken. One thing that I do, I think there was at least one talk earlier in the morning that kind of connects to this. You don't necessarily have to generate new concept set every time. You could potentially use things like scene graph representations and amortize and slowly establish like a common ground vocabulary between the humans and the machines, and then build on top of that, so that can kind of reduce the amount of work that you do. Grounding the concept set, of course, is learning the denotation. And as I said, vocabulary expansion is actually a more interesting thing, and I'll refer you to the paper for some of our initial ideas on that. The first and second challenges have actually been considered to some extent in making sure that the explanations and the advice are taken by the systems that we have built. Okay, so that's the agenda that I think I have sort of rushed through. And so in summary, we started with kind of a model-based comparison of planning versus RL. It's kind of a different kind of a comparison than some of you might have been used to. I hope it kind of helped some of you to get slightly different insights about the differences between RL and planning. We argued that RL system should support a kind of a symbolic interface of communication with humans, irrespective of whether they're using symbolic models or not. If they're using symbolic models, well and good. If not, you better be ready to convert the representation as needed. And then we discussed how symbolic planning that we know of, can play a role here. The advice can become partial symbolic models, for example. And we illustrated some of the potential solutions in a couple of systems that we built: Blackbox and iClear, iExpand in Neurips, SGRL in ICML this year, and then that SFEBL, EBL, which is in the III workshop on RL and games. And of course, there's all sorts of interesting philosophical questions that you can get into, such as if you actually develop a symbolic interface to talk to humans, would you eventually start doing your reasoning also in that interface, as against having two different lives? I won't talk about that right now, but I will stop here, and if there's any time, I'll be happy to take any questions. Thank you.
Okay, thank you so much. You have time for questions. Please raise your hands.
Go ahead, Hector.
Thank you, Rao. It's always a pleasure to have you here. Okay, so it seems that you are assuming that there is a hidden model and a sort of a fixed hidden model. When you said, when you talk in terms of efficiency, I know you said these both things about the internal model, and then maybe you have a DVL that may have some symbols internally for efficiency. But then when you talk about explanations and you talk about the communication, it seems that this is hidden assumption that there is like a model, right?
No, it's the model that I'm talking about is the model that the human has in their mind, which in our terminology is MRH, which is what the human thinks the robot's model is. When we are trying to work with any decision-making system, there's enough folk psychological evidence saying that decision-making systems are thought of in terms of preconditions and effects, even outside of planning, even outside of ICAPS community. So all the explanation is with respect to a single model, although we have done earlier work showing that if in fact there is uncertainty about which of 5 different models the human might be having, you can provide the best explanation in a Bayesian sense. There's a very nice paper that Sharath had written, I think, 2 years back in ICAPS, about a Bayesian account of interpretability and explanations that actually takes into account a distribution over MRH. And so that aspect of whether or not it's a single model is not important. In this case, we did that as if there is a single model, but it can be extended if there is uncertainty around the models. But and you know that from the advice point of view, the partial model might correspond to many possible complete models, and that already allows for sets. And it's the same thing in both sides. And so you can actually. The only point is it's better to take advice that humans who have expertise in the domain have come up with than to just say, no, I'm going to do it all by myself. And that's basically the only argument that I'm sticking to. And, there may be corner cases where the humans are so bad about this domain that they really completely put the machine in the wrong direction. But really, how much do you believe that the same technology that is getting these robots to control their 20 joints for a little amount of time will actually work without changes to long-term planning? I mean, you already saw the huge problems with the kind of in extending them when Sergey was talking this morning, because there are all sorts of interesting efficiency issues that will come up. And so if there is expertise, let no expertise be spurned is basically what I think ICAPS should basically say, because that's what we kind of tend to use. But let no expertise be seen as complete and correct either. And so in some sense, RL can provide robustness over the human models. Yeah.
Yes, but
Yes.
so when I have a planner, something I can do. I mean, if I solve two instances if I solve two planning problems one after the other, even in the PDL, it's very similar. I may have different intentions. Like in this case, I want to solve these problems, and now I want to solve a variation of that. For instance, I can solve logistic problems, and then after that, I said, you know what? I don't want to use the planes today because I don't know, there is a volcano. So I want to say that even if I have been solving all my life logistics with trucks and planes today, I don't want to use planes. Why? Because I decided to do so. So that is not a hint. That is not advice. And they
no, that's preference. Preferences can be provided as advice. Right? Basically, in the expand system, I can basically tell you that today, please don't use. I mean, there's no real reason why advice has to be given once and you leave the RL system on its own forever and ever. I actually already showed you two advice systems, one where the human is present during the training, the other human just gives a partial model. There is a spectrum. I can change the partial model tomorrow saying, today I'm not feeling like planes. And that's advice. And so it's not a big deal. I mean, my point is that you can't do worse than what other systems are already doing, which is every time the reward metric changes, it's a new problem. And we take credit for generalizing. For the crying out loud, nobody ever took credit for generalizing from 4 blocks to 5 blocks problem in PDL, right? It's just because the model exists and you have the interactions taken care of. So it's actually advantageous to provide the model, partial model for today. If I have extra constraints, then I provide that day, and that should be fine. And that's basically my stance on that.
Okay, got it. It's just that so you are sort of confounding like assumptions with advice, and I don't feel.
I mean, no, I'm using the word advice in a very loose sense. What the human wants the planner to do, for what reason, can be for efficiency reasons, can be for their preferences, can be for safety. But if the humans ask you, you do it.
Okay.
Because your radiation support system with the human in the loop. So that's what I mean by advice.
Okay, good. Anybody else?
More questions?
I can ask questions. So there have been a lot of work in the RL community on providing additional information, right? Like what you have talked about with additional models, additional symbolic models that you put on top of basically on top of RL. Right? Lots of work recently on that. But there was also work on providing information about the solutions themselves, right? So there is a difference between providing declarative models, like planning models, and providing advice on how to solve the problem or solutions, basically, using something like LTL, right?
Yeah. No, but again,
what do you think about that and the differences between the two approaches? And
so two different points. First, my first part of my answer is the same as what I gave to Hector. I am allowing any kind of advice, even if in fact that advice is about solution, and how to find the solution. Because imagine what happens in expand, where the system took a particular action, RL is about to take a particular action in a particular state, the human says, don't do that, do this action instead. That's a way I can essentially hold your hands and take you anywhere I want. Okay. So I know that from a planning community perspective, we differentiated the advice about dynamics from the advice about preferences, from the advice about the solution, from the preferences and dynamics, we tended to separate. But I am actually allowing by advice, I mean both of them. And as to what I think about it, I mean, if I really want a particular kind of solution, because I have a hidden preference for that, I mean, you are going to do it, right? Basically, if I tell my travel agent, when we used to have travel agents, that, make sure that I only have 1.5 hours in Philadelphia because I hate Philadelphia Airport. I mean, because I won't tell them why I hate Philadelphia Airport. And then make sure that I don't fly on, I take Southwest to get in and use Delta to get out. They can find a plan which actually satisfies those. And if they say, no, we won't, then I'll find another planning, travel agent, right? So my sense is that I'm not taking a particular stance on whether the advice should be about dynamics or preferences. In fact, there is a slide which says advice can be about preferences or dynamics, basically anything that the human cares about are representations. In fact, the advice can also be just about the things, the fluids I care about in this domain are the following. In fact, one guy this morning was talking about, standardizing the fluids at a lower level and then going from there hierarchically to a higher level fluids. There, essentially, the human has provided advice in terms of the fluids that they care about. And so somebody essentially looked at the pixel space and converted to those particular fluids. So the state has been extracted that way. So that's a particular kind of advice from the humans, saying, look at this world only in terms of these fluids. And I think, in fact, I expand the scope. I mean, in fact, in normal planning community, we never even talked about that because we don't talk about, we are increasing the vocabulary. We now have RL agents, basically, especially those that come from, essentially learning from the space-time signal cubes, like images or whatever. They can come up with concepts that don't actually have any connection to anything that you necessarily have named for. Okay, and that will be fine. And all I care about is during the interaction, either you give me an explanation that I understand, or we both work together to expand my vocabulary. And that's basically the other aspect where, figuring out why did AlphaGo do the third term. Is there something that I can provide as a reason as to why it provided that?
So I think it's very important to keep the distinction between this is optional, this is separation, host and system related, because at the end of the day, many of the difference in the technique are going to depend on that. If
except in case of RL, we pretty much are using all of these as soft constraints.
Yes,
okay. In fact, we were having this exact consideration. In fact, in the paper that I mentioned, the SGRL, it's actually a soft constraint. The symbolic model becomes a soft constraint, and it was us, the planning community and the logic-oriented communities, who cared about is the advice binding or not binding. And you can always, and if it is binding, then completeness can be lost. Okay. But you can always make sure the completeness holds by saying it's a soft advice. And soft advice basically means you look at those actions before the other actions. So you're more likely to get to this policy before the other policy. And you might say, can you give a proof? When was the last time there were proofs about any policies that the RL systems are finding? it's also a separate mindset that we have to get used to. We tend to think in terms of, is this particular optimal plan actually going to be coming? Instead, we talk, in RL at best, the good RL, the theoretical RL tend to think in terms of can you bound the loss? That's about it. They're not going to actually talk about whether or not, how many different places would you have a different action in the policy compared to this other. You could do it, but that's not normally how, most of the popular, the DRL systems that capture public imagination do. So using this as soft, constraints is the name of the game. And in fact, actually, it's become interesting, right? I think Sergey was talking about this SECAN paper, and I don't know if any of you have looked at it. It's crazy. Basically, SECAN tries to generate some random ideas for possibly what the next action would be, because presumably Palm thinks that these might be the actions given, this is the prompt for the current plan. And then they may not actually make any sense at all, and somebody has to check whether they make sense or not. So the planner has to cut down the possibilities. And efficiency is something that, I think the pure RL is so damn inefficient compared to planning that you can come up with lots and lots of ideas that do better than pure RL. Okay? And so that's just the reality. In fact, you guys heard that. One of the things that it's similar to the kind of work that gets done, that I don't know, I have an onion in front of me, I don't know what I'm supposed to do with it. I'll think about my experience, and there seems to be a higher value state where I had a knife. That's actually extremely, unboundedly inefficient way of doing reasoning, because there are humongous number of high value states in my past, and none of them are relevant to cutting the damn onion. And we spend tons and tons of time making sure that what we're doing is kind of relevant, and we cut out all the irrelevant actions, etc., etc. You want to actually combine these, you have to consider what people do and what people push under the rug. We do certain things, we push under the rug and other things. The same with RL, and you need to have a good understanding to actually build the bridge. Otherwise, what you will have is RL envy and planning obliviousness, and that's not very good.
Good point.
Wonderful. Thank you.
Thank you.
Hey.
Yes, thanks. Very nice talk.
Thank you.
And there was a lot of information, very interesting papers that they got to Neurips and ICML and ICLR, which you don't see very often, this type of work there. So I could ask about many of them, but maybe I should read them in detail before asking. So in one of them, you were showing a graphical model. Maybe you can give some details.
Which one?
About that, the confidence level, the last one, the ICLR paper.
Yeah, actually, to get to that, you have to give more of the detail of the paper, but essentially, in trying to compute, sort of, at a high level, imagine Lime is trying to figure out which of the linear approximations are the best around this particular decision, and it's trying to attach confidence in terms of the fit. More or less, something like that is what we wind up doing. To actually give a good technical answer, I need to actually walk you through that data.
Okay. Well, thanks a lot.
Thank you very much.
Okay, so let's thank the speaker again. Thank you so much.
Thank you.
So we are switching to the last session of our workshop, and this is about discussion, closing remarks. And